Recording is rolling. It is Tuesday, February 13th. We're going to wrap up these chapter 13 puzzles today. If you finish with these by the end of class and you feel good about all the ones that I've circled down in class, you can turn this into the gray tray and I'll get the score for you guys. If you're not, if maybe you like missed a day or you're not sure about some of these, you want to turn it tomorrow, then that's okay too. Right. So here's chapter 13. The other day we did these three, 80, 84, and 90. And today we're going to finish with these four, 93, 108, and then these, well, the two pie questions at the end. Okay. Don't worry about the ones that we skipped. Okay. Same thing with chapter 12. Chapter 12 we did back, I think last week. We just did 6 of those, right? Just those 6 I circled over there. Okay. Okay. And then the rest of this week, I've got activities for you guys. Tomorrow is going to be Archimedes Principle Buoyancy Lab. Right, so I'll show you guys today what that set is, so you have a day to think about it, sleep on it. And then Thursday, Friday, I've got a SIP project. Right, I'll show you guys a little bit about that later in class today too. So fun-filled day. Number 93. How much longer will a so many meters long steel bridge be on a hot day in August compared to a cold night in January? Right? And I gave you, it says alpha for steel. That represents the coefficient of thermal expansion. Right? Just like all these puzzles, my numbers are different than your numbers, but that's like we all have the same premise. Right? And so I'm thinking about this poster right here that you guys saw the other day, something about thermal expansion. Right? Now this is showing linear thermal expansion. Maybe to go back and retitle this. There's a version of this too. You can think in 3 dimensions. Think, well, it doesn't just expand like lengthwise from a temperature change. It can also like what about like depth and height or something. That could change a little bit too, right? But if you have something that's kind of long, maybe like a beam or a column, or in this case a bridge, right? Maybe it's like mostly the length increase that I care about from a temperature change, right? That's what this equation down here says. It says the change in length, so in this case like the thermal expansion in the linear sense, linear thermal expansion, is equal to the original length, right, L, times, delta T could be the change in temperature, right? And this alpha is the coefficient of thermal expansion. Now that's a material property, right? So different materials will expand differently from different temperature increases, right? Or every once in a while you get a material that actually shrinks from a temperature increase, right? Now that's really rare, but like one of those examples, which is kind of a counterexample to the rule, could be like water going from a liquid to a solid form, freezes, actually expands, right? It's kind of weird, right? But the general rule is, yeah, most materials, you heat them up, they expand. Right? You guys might remember also, I was making a whole big deal the other day about the fact that steel and concrete happen to have pretty much the same coefficient of thermal expansion. Right? There's like a window of values. There's different types of steel, different kind of concrete. Right? But what that means is that you can create steel reinforced concrete that will actually last for many years, right? Because if they had different rates of expansion, then your structure would crack apart pretty fast, right? The fact that they expand and contract together with the same temperature change, right? You can create steel reinforced concrete also. All right, so put that together and solve the steel bridge. Number 93. Okay. So I'm going to say the change in length, which we're solving for, right? How much longer is the bridge going to be, okay, is equal to the original length multiplied by coefficient of thermal expansion multiplied by the change in temperature. Okay. Right, so now my bridge was 200 meters long. I've got a coefficient of thermal expansion for steel of, now this says 12 times 10 to the negative 6. Okay. And then the unit is 1/Kelvin. Great. And then change in temperature. Right. Well, I gave you guys 2 temperatures. Okay, so they could be like final minus initial or something like that. Let's go say from the cold day to the hot day. Right. So my hot day is 25 degrees Celsius. My cold day was 3 degrees Celsius. There's my change in temperature represented right there. Okay, you guys got that? Okay. Now, how many guys are maybe saying, well, hold on, actually, does this work in terms of the units, right? So change length is probably going to be some number of meters, so that's set up there. It's all fine and good. Right? What about these temperatures? Right? 1/Kelvin versus something in Celsius, right? I'm gonna make a whole deal too about like if you scale up or down temperature by some factor, say like ideal gas law, or for example, you have to use Kelvin all the time. Do we have to convert this to Kelvin first, or is it okay that I leave this in Celsius? How many guys think it's okay that I just go ahead and leave this in Celsius? It's okay, right? Right? Because it's not a hard value. It's a change. It's a change, right? Do you guys remember too, guys? Is a change in 1 degree Celsius the same thing as a change in 1 Kelvin? Right? Yeah, it's the same thing, right? So even if you convert this to Kelvin first, the difference would still be the same value. For me, that'd be 22 degrees Celsius or 22 Kelvin change would be the same either way, right? So as long as you have a temperature change, it's okay to leave it at Celsius, right? So I got that times that, right? You guys are trying this out too, your calculator. Make sure you get the correct answer. Okay. So I'm getting a small number. Right? Guys, that's a small number of what? What's the unit? Meters, right? Right? Because base SI unit meters, right? No, maybe it's better to think of it in terms of like centimeters, maybe. Right? So how many centimeters is that? 5.28 centimeters, right? And actually, my answer choices are got in millimeters, so let's see that too. Right? That'd be like 52.8 millimeters, like that. Okay. Remember, the ruler on your desk is 30 centimeters long. So good idea there. Right. All right. So you guys getting an answer choice on your paper? Mm-hmm. All right. You guys ready for your next one? So, all right. 108. A hydraulic lift. Ah, look at that hydraulic lift. You have a poster up here that says something about Pascal's principle. Has hydraulic lift on it. Pascal's principle. You guys think it's coming up? All right. We're trying to lift a car. So I'm going to call it the output force F2. And ooh, I listed how many newtons that is, right? Okay, so that could be a weight measured in newtons, right? The diameter of the large piston is so many meters, and the diameter of the small piston is so many meters. What input force is required to lift the car? Right? Okay, and I said each piston has a circular cross section. Even if that wasn't true, the answer would still be the same in the end. Right? Okay, notice I gave you the diameters, not the cross-sectional areas. So I'm throwing in an extra step, right? So is it 108? Okay. So you guys remember Pascal's principle? Says that the pressure in a fluid is transmitted undiminished. So this hydraulic fluid down here, the pressure is the same everywhere. You think of it like that. Right? Same pressure everywhere. Right? And what is pressure? Well, I remember last semester it's like force per unit area. So force per unit area, right, is equal to the pressure. Maybe we're adding in the hydraulic fluid, right? And then that's the same on both ends of that hydraulic lift. So I'll go input, input, output, output. F1, A1, F2, A2. Okay. Okay, so what did I give you and what are we trying to find here? I told you the weight of the car, so that's going to be F2. I'm saying what's the input force? That's like F1 we're solving for ultimately. Right? I didn't actually give you the areas of those pistons. I gave you their diameters. Right? So we're going to have to do some side math here, side thought. Right? What is here, no, this over here. So here, oh no, paper. Okay. What is the area of a circle in terms of its diameter? It's like the circle has like some diameter. Right?
I thought d over 2 squared.
Okay, yeah. Let's do that. Right. So I know the diameter is twice the radius. Right. I know area of a circle, so cross-sectional area. Area of that circle is true. It'd be say pi r squared, but I'm trying to think of it in terms of diameter. So that would be what was that? Diameter over 2 squared. Right. What Adam came up with, right? Like that, right? Okay, and then okay, that 2 we can square that and bring it out in front in the denominator. So could that be like this? Area of a circle is pi over 4 times diameter squared. You do it like that, right? Yeah, right. Maybe that's a good one to know, right? Definitely know the area of a circle in terms of its radius. Right? Gotta know that before you graduate high school. Right? In terms of its diameter, I think I remember seeing this. I think for the first time I was sitting in some engineering class and we were talking about like pipes and there's this pipe diameter, blah blah. Blah. Right? The instructors like wrote this on the board, kept going, and this is the first time I'd ever seen it. And some other students were like, "Where's he getting the pi over 4 from?" I said, I gotta figure that out. Oh, okay, I see. That connection with the radius of the circle. Okay. All right, so there you go. So we're gonna take that right there. We're gonna substitute right there. So let's do the input force over pi on 4 d squared, the input squared, is equal to, and the output force on pi on 4, the output squared. Okay, that's true too. Right, guys. But what you are probably seeing anyway is that is the pi over 4 going to cancel out both sides anyway? Yeah. Right. So what's important though, it is important we did that anyway because the area that we care about is proportional to the square of the diameter. Right. So you do have to square the diameter. Right. So maybe I can say this: the cross-sectional area is proportional to diameter squared. Right. So even if these pistons were like a rectangular shape or a square shape or like some funky shape, right? Then yeah, you can still apply this principle, and it's important that you just like square the diameter, right? So pi over 4 has to do with the circle shape, right? That just cancels out. And so let's plug some numbers in. So I'm solving for the input force. Right? Now the input diameter on mine was 0.25 meters. Right, I have to square that. Right? And then the output force, I'm trying to lift a car that's this many newtons. Right? And the diameter piston that car is sitting on is this many meters. Right? And then square that to turn that into some form of an area, cross-sectional area. Right, there we go. And then last step, all I have to do is cross multiply this input diameter squared. Boom, I got the answer. Right, so cross multiply that, what do we get? So the input force is, right, so here's the weight of the car times that square divided by that square. Looking at maybe this many, that many what? What's the unit? Newtons, because it's a force in newtons, right? Also square meters cancel. You're left with newtons. Yeah. Right. Check, make sure you're getting an answer choice on your paper that matches your math. Yeah, all right, I got it. Answer choice right there. Boom. Go. So that working out for you guys too. All right, everybody right? Oh, cross multiply. Yeah. All right, so here, I'm just gonna take this 0.25 meters being squared, right, and multiply it up here. Right. So it's gonna look like looks like 14,000 newtons times 0.25 meters and then being squared, all divided by 4 meters being squared. So my numbers look like that. There you go. There's cross multiplication. Just take this denominator, move it to the other guy's numerator. Cross multiply. All right. All right, working out. Yeah. Yep. All right, you guys good on Pascal? Good on Pascal? All right. So now we got these last two questions, which go together. They both talk about this pipe system. There's water flowing through this pipe system, and it's going from a wide pipe into a skinny pipe, right? Is that wide pipe into a skinny pipe? Okay. So the first question is a conservation of flow question. It says, what's the speed through the skinny pipe? If I give you enough information to solve that, right? And the follow-up question is going to be, what's the internal pressure? Right? Which is a Bernoulli's principle question. Right? Now you can't answer the second question until you answer the first question. So even if I only asked you the Bernoulli question, you'd still have to get conservation flow first so that you can answer it. Okay. So yeah, so the first question is the setup for the second question. Here we got water flow through a horizontal pipe system. Right? That's going to help us out later. The fact that it's horizontal, there's no height change. Right? Okay, so here I've got the cross-sectional area for the wide pipe, right? And the speed of the water going through the wide pipe. Right? Then I gave you guys the cross-sectional area of the narrow pipe. Right? And then what's the speed of the water flowing through the narrow part pipe? Again, like I was saying a few minutes ago, a lot of times pipes are listed in terms of their diameter, right? So it might be common to be given the diameter. So you have to do what we did with this hydraulic lift, is convert that to an area first by somebody like pi over 4 times diameter squared. Right? It's common with pipes, right? But I gave you the area, so that'll save us a little bit of time, right? So B1 solid. Okay. So this is going to be conservation of flow, right? Which looks like this. You might remember this from the other day, or maybe see it on one of these posters. A1 V1 equals A2 V2, right? Area times velocity is that product is the same everywhere in that pipe system. Okay? I want to remind you guys why that's true, kind of where that comes from. It comes from a flow rate, right? Like area, let's think in terms of units. Could that be like some number of square meters, and velocity could be meters per second, right? And then this area could also be in square meters, and this velocity is in meters per second, right? Put it all together, doesn't that represent some number of cubic meters per second, right? In terms of units, cubic meters per second, right? Hey, is that kind of like gallons per minute, right? Gallons per minute, cubic meters per second. It's the same concept, right? It's a flow rate, right? So that flow rate has to be the same everywhere. And there's one more technical detail to make this true, and that's that water is basically not compressible. You can push and push and push on water, give it like a huge pressure. It does not change its volume, right? If it did, I'd throw in one more factor here for density of the fluid, but we're not going to do that for water, right? So that's it. Right? So I gave you 3 of those 4 values. All we got to do is solve for the one unknown, which is like this V2 right here, because we have everything else. Right? You guys get the setup? All right, so let's pop some numbers in. My first area was this many square meters. It was going at the speed of this many meters per second. Okay. And then it went into this narrow pipe, which is, well, on my paper, it's this many square meters. I'm solving for, well, how fast it's going through. All right, divide that over. I'm getting speed is this many meters per second. Okay. Oh, maybe I should have asked you guys before I started too. Right? When the water goes from the wide pipe into the skinny pipe, does it have to slow down or speed up? You guys would have said what? Speeds up, right? Speeds up, right? So okay, so that shows up in the math. Right? In fact, I have a pipe that's 1/4 of the cross-sectional area. It has to be going 4 times as fast for this conservation of flow. Right? Yeah, you guys know that too, right? Yeah, has to speed up going through the skinny part of the pipe for conservation of flow. Right? Right, you guys get there? You guys get an answer choice all here? Right, so then the follow-up question. Okay, again, you had to get that question right to get this next question. Okay, is what happens to the internal pressure? So now let's imagine you're a fish swimming around in this pipe system. Fish swim around. Right? Kind of like if you're swimming around the pool, feel some pressure on you. Right? And that pressure is going to change when you go through this skinny part of the pipe. Right? What do you guys think is going to happen to the pressure from the wide pipe to the skinny pipe? Does the pressure increase or decrease? How about this? How about the question we just answered? The water speeds up, right? Speeds up, right? And do you guys remember? No, let's do this again. You guys remember if I blow a stream of air over this paper, what does it do? Does it push it down or vacuum it up? It's vacuuming it up, right? Good. So a moving fluid causes an increase or a decrease in pressure? A decrease, right? Because you just saw it vacuum up, right? It decreases the pressure because it vacuums. Okay. So back to the pipe system, the water speeds up through the skinny pipe. Therefore, what happens to the pressure in the skinny pipe? Decrease, right? Right. So I bet if there was a fish just like swimming through the pipe system, I bet it's going to feel a pressure decrease. You know, kind of like it went from the bottom of the pool to the top of the pool, right? Let's try the math and see if the math agrees with that. So Bernoulli two. Okay. So I'm going to list out Bernoulli's principle. Okay. Now this one's going to start kind of long. I'm going to use the full width of this paper. We got. You guys remember this is basically conservation of energy just in terms of pressure units. So there's some internal pressure in that pipe system, right? So the water feels the fish feels some pressure on them, right? Swim through. Right? And then I'll say plus rho GH initial plus 1/2 rho V initial squared, okay, equals some other internal pressure, pressure final, plus rho GH final plus 1/2 rho V final squared. Right? So Bernoulli's principle, the kind of fundamental version of it has these 6 terms, right? And they're all in terms of pressure. Again, this looks a lot like conservation of energy. I remember back, okay, let's think way back a few months ago, conservation of energy. Right? It could be like some form of energy, maybe like spring energy or something, right? And it could be energy of height, like mgh. There could be kinetic energy, energy motion 1/2 mv squared. You guys know that? Okay, so if you just start with basically conservation of energy, and then you divide every single term by volume, right? Well, guys, what is mass divided by volume? Density. Hey, that's what that is right there. That's Greek letter rho density, right? And oh, also right there, instead of 1/2 mv squared, it's 1/2 rho v squared. So, right, so it's mass over volume. You do that for all 6 terms. If you take just in general energy divided by volume, that gives you pressure units. Okay, you guys see where that comes from? Okay, everybody, right. So next step I want to do is say that the fact that this pipe system is horizontally oriented is going to help us out, right? Because if it was vertical, kind of like if you swim from the bottom of the pool to the top of the pool, there's a pressure change because of a height change, right? Which could add, okay, but that's taken care of here in the Bernoulli principle anyway. But the fact that we have a horizontally oriented pipe system means that from here to here, there's basically no height change, right? Or you could think of it this way: this height is this height, right? So can we just do this? Can we go, right, and narrow this down from 6 terms down to 4? Right? Okay, so now we're only working with 4 terms, so it's easier to work with. Okay. And should be enough information we can ultimately solve for what is the internal pressure, say like on the fish swimming through the narrow part of the pipe. Okay. So I gave you the pressure in the wide pipe. Now mine says 300,000 pascals. So I'm gonna pop that in right here, 300,000 pascals, right? Now let's put some context to that number. Great, that's a big number. What does that mean? Right? Because right now we're sitting in Earth's atmosphere pretty near sea level. Right? We're definitely not in the vacuum of space. Right? So how much pressure is on us right now? Well, you could quantify that 1 atmosphere. And guys, 1 atmosphere, how many pascals is 1 atmosphere? Who remembers? How many pascals is 1 atmosphere? That's right, a lot. It's about 100,000. So call it 101,300 something, right? Guys, this, your largest lab weight, this is 10 newtons, right? 10 newtons of weight, right? No, that's weight, right? 10 newtons weight, right? Imagine 100,000 newtons. Here's 10, imagine 100,000 acting on 1 square meter. That is how much pressure we are sitting in right now, right? Compared to vacuum space, right? This fish at 300,000 pascals, how many atmospheres is that? 3, basically 3, right? Round a little bit. Okay. Yeah. So here's my fish swimming through, and he feels like he's at 3 atmospheres of pressure. He's going to go through the skinny part of the pipe. The pressure is going to drop, right? I wonder how much it's going to drop. Well, that depends how much it speeds up, and we just solved that from the last question. So let's start plugging in numbers. Ooh, guys, what is the density of water? What number I'm going to plug in right there? Density of water, what is that? Is that an even 1,000 kilogram per cubic meter? Remember back in the 1790s in France? Well, I was there, you guys. They were saying, well, how are we going to define what is the kilogram? Hey, let's fill a box with water and call water like this exact density, and then that'll define the kilogram. Right? That was the original back in the day. And then, I need the original speed. Now I gave you that the previous question, so I'm going to copy that number right there. Okay. So mine is this many meters per second. And don't forget to square that speed. This is all equal to some final internal pressure that we're solving for. I'm going to skip over the rho GH that canceled out. Right, so plus 1/2 times this density is also 1,000 kilogram per cubic meter. Right, remember, we're going to call water not compressible. Right, times, the final speed squared. Right, and what was that final speed? Oh, that was the answer to the last question. That's why we did that question. It's that conservation of flow. It was a setup for this Bernoulli. Right? So I'm going to take my answer to the previous question, which was for mine was 36 meters per second. Okay, and pop that in right there. Okay, just like that. Okay. Right. And of course, you guys have your own numbers. It's working so far. Okay.
Where did you get the 9?
Okay, this 9 meters per second. That was the original speed in the wide pipe. I got that from right here. Okay, yeah, it's the original speed in wide pipe. All right. So it's working out for you guys. Okay. All right, so all I gotta do is multiply this up in my calculator and then subtract this term over here. I'll break that down in 2 steps. Let's go 300,000 pascals, just the original internal pressure, plus its some pressure sort of went to its motion, think of it that way. So 1/2 times 1,000 times pressure. Looking at 40,500 pascals right there, right? Equals pressure final plus, and I get a number for this. Getting, woo, big old number. Okay. Okay. All right, so that plus that minus that is the answer. Pressure final equals, see what I'm getting, what is that many pascals of pressure plus that many pascals minus that many pascals. Okay. Oh. I'm getting a negative number. Right. Are you guys also possibly getting a negative number? Can you have a negative pressure? Yeah, you can. Right, it's great. It's like the water's trying to like pull everything apart. Right. So yeah, this liquid water, yeah, it sure can. It can have a negative pressure. Could I call that? Roll back the decimal 3 places and call it kilopascals. Can I do that too? kPa, kilopascals. Right. Something that like that. Right, which is an answer choice on the paper. So I'm all good to go. Right. Okay. Now, another detail I want to add to the story. Right. What do you guys know happens to water when you lower the pressure too much? What does it start to do? Boil. Right. And what is that called in a pipe system when the water goes so fast that the pressure drops so low that it starts to boil? What's that going to do to your pipe system?
Probably break it.
Yeah, probably break it. All right. That's what I was looking for. There's kind of a technical term for that. Oh, is this not gonna present? Right. Called cavitation. Right. Here's cavitation inside a pump. Sometimes this happens inside pumps. You get these narrow parts where water's flowing through, it goes too fast, and the pressure drops too low, blah, blah, right? Yeah, so it's yeah, exactly. It's tearing up in this case this pump system, right? Yeah, so if you're maybe like engineer one day, putting something together and like cavitation bubbles and getting all your equipment all all cavitating, think, okay, well, that's probably what's going on. That's probably what's going on. Okay. There's cavitation right there. All right. I want yeah. Huh?
How do you fix that?
How do you fix that? Well, yeah, I guess if you replace that part with an identical part, then you're kind of asking for the same thing to eventually happen, right?
Yeah.
But if you maybe can widen your pipe enough, like what could narrow a pipe in the first place? It might just be that you put it on too small a pipe, or it might be that maybe there's maybe the pipes start to get clogged, right? And so then that's causing the water to like go through faster, and that causes this process, right? Yeah, or maybe you need a new part that maybe if the water doesn't flow as fast through, right, then there won't be as much of a pressure drop. Or if you widen the pipe enough, right, that could do it too, right? So yeah, those are all little fixes, right? Think about those equations we just did. Right? What variables you could guide you through? Say like, how can I make a change? I can have a wider pipe. I could have like less water flowing through. Right? Those could be a couple fixes like that, right?
Okay.
Right, now there's another slide I want to show you guys. Ooh, okay, it's another presentation. Here it is. Here it is. Right, it's right here. Right, so the rest of this week, I'm going to do projects with you guys. Now tomorrow we're going to do a Archimedes principle buoyancy lab. Right, so I'll show you guys that too. Right, but Thursday and Friday, I'm going to have you guys build a sieve. Okay, so what is a sieve and what's it good for? So say you got oh, here we go. I got these concrete cylinders, right? I think these are, if I remember right, 4 inches in diameter and like 8 inches tall, right? And you can put them in this hydraulic press and like smash them until they break, right? You can tell you what is the compressive strength of that concrete, right? Now, notice we're focused on compressive strength for concrete, not tensile strength, because tensile strength it has almost none, right? You pull on it, pops apart real easy, but you can press and press and press, right? And here I'm getting from this table somewhere between like 2,000 and 5,000 like pounds per square inch. And here in the margin, I translated that to megapascals for like metric, right? Somewhere about 17 to 30 something megapascals, or maybe this many atmospheres, right? If you like that too, right? And how can you get different strengths in concrete? Well, different ratios of these ingredients, right? Is one way to think about it. Right. But another factor that can go into concrete strength is the relative size of your aggregate, right? Relative size of your aggregate. So think about this. What if you had so what goes into your concrete? So you got aggregate, so basically think rocks, right? Or it could be sand. Right? You have cement, like Portland cement and water, and it goes through this chemical process and it cures and it creates your concrete, right? But that aggregate is going to be the strongest part of your concrete, right? And the cement is going to be a weaker part. Well, what if you had all the same size rocks? Right? Think about this for Thursday and Friday, all the same size rocks. Well, then you'd have like pretty large sized gaps that are just filled with concrete that's weaker, and that's going to be the weak part that's going to break first, right? But what if you could take some of these gaps, you could fill them with like medium sized rocks? Ooh, now you have a stronger concrete. Well, now there's gaps between the medium rocks. Okay, now you have little tiny rocks, maybe like sand grains, right? Okay, now you have stronger concrete. You can fill those gaps with like little silt and clay particles. Now you have stronger concrete, right? So you guys see the strongest concrete you can have is has this well-graded aggregate, right? You want large rocks and medium rocks and small rocks and sand, right? If it's poorly graded, also called uniformly graded, that's only one size aggregate, and you got a lot of cement, now it's relatively weaker, right? Some is gap graded, maybe has large to small, but nothing medium. That's not as good as well graded either, right? Here's is on a graph, right? Well, how do you know that your aggregate is well graded, right? Okay, well, you can use a sieve, right? So here I have a stack of these, and they all have different size wire mesh. You guys see this wire mesh, right? Now the large wire mesh you put near the top, and only the large aggregate is held behind, and everything else goes through, right? And then by the time you get to smaller, you have successively smaller size mesh, right? And then the very bottom, right, only only a little like silt and clay gets through, right? Right. And if each one of these sieves captures like some good proportion of the aggregate, right, then it can be well graded, and that could be an indication that you're going to get like pretty strong concrete, right? Or what if like a couple of these sieves are like catching nothing, right? So you got large and small, right? Well, that would be gap graded, and then you can fix your aggregate. You say, okay, well, let's just get some like medium size, like little pebbles, and then put that in there, like put it in the mix. Right? Now we have something that's well graded, right? So we're gonna construct that, and I'll have you guys test this too. I'll give you guys a sample, and you can use your sieve. So that'll be Thursday, Friday. Okay, but tomorrow, I've got for you guys a buoyancy lab. Gonna have you guys build a box boat. So rest of the day, I'll guide you guys through this so you guys know exactly what you're looking at for tomorrow. Okay. So box boat buoyancy lab. I'll give you guys this page. Oh, this page is double-sided. Here, let me zoom out for you guys and see the whole thing. Okay. So side 1, side 2. Have you guys make a couple of graphs, right? I'll show you guys everything that's going on today. Right? So again, you have a night to sleep on this. Think about it. You guys come in tomorrow. Okay, know exactly how it's going. Right? Whatever notes you guys are taking right now, maybe help you out tomorrow. Right? So design a box boat with the given materials to maximize the weight that the boat can carry. Right? Pretty much all I'm going to give you guys is 1 square of aluminum. It's going to be 12 centimeters by 12 centimeters. So I don't have it right now, but I'll have it tomorrow. I'll give you guys a sheet of aluminum. Right? That's 12 by 12. Right? I'll give you guys a bucket of water. Right? Right? Now, if you just throw the sheet of aluminum in the bucket of water, right? Maybe it floats from surface tension, but that's about it, right? You throw a little tiny blob on it, it's going to sink, right? Okay, so hey, maybe you bend up the sides, right? You guys see this, right? And I'm going to call that some amount X. So you start bending up the sides, maybe bend up like 1 centimeter, right? Okay, so now you got a boat, right? And then you start stacking in lab weights, and I can hold like some amount of weight. Say, hey, I wonder if I can hold more than that. What if you bend up the sides like 2 centimeters or 3 centimeters or 1.5 centimeters? Right? You could try different different values that could bend sides, right? You're always gonna have this square box boat, right? How can you maximize the amount of weight they can carry? Right? You guys get that premise? Right, so let's go through these questions then. Right? Draw a free body diagram for the floating boat. This could be a side view, right? Like here's a 3D shot, right? But what if you're looking at like from the side, right? Okay, so that's like this view looking from the side, right? Ooh, do you guys think what force is trying to drag it down, make it sink? About the weight, right? What all the weights that you're putting in it. Okay. What force is holding it up and preventing it from sinking? How about the buoyant force, right? Ooh, is that like Archimedes' principle? You guys see one of these posters up here? It says Archimedes' principle. Okay. It's got thumbnail notes, right? Okay, so then buoyant force. Oh, okay, that breaks down into, guys, what times what times what is buoyant force? Remember, buoyant force represents the weight of, in this case, the water that's being displaced. And you can break that down into the density of water times the volume displaced times gravity field. Okay, that's what that's gonna be. So tomorrow, right? You guys gonna remember that for tomorrow, right? Whatever notes you're taking right now, you need to help you out, right? Then the actual lab weight you stick in here, okay, that could be mass times gravity field. We've been using that since the beginning of this class, right? Okay. Ooh, what is the density of water? And I gave you 2 different units to think of it in terms of, because depending on how you do this math, right, might be easier to use one or the other of these. Guys, how many grams per cubic centimeter? Suppose you have a box that's 1 centimeter by 1 centimeter by 1 centimeter, little tiny box, and you fill up with water. How many grams is that? 1. It's 1 gram per cubic centimeter. Okay. Now, if you have a cubic meter, no, that'd be a big old box. That's like a meter stick by a meter stick by a meter stick. Filled it out with water. How many kilograms is that? 1,000. 1,000 kilogram cubic meter. Right. We used that just a few minutes ago. Right. We saw one Bernoulli. Right. What is a gravity field? Right. How about meters per second squared? Could you say either 9.8 or 10 meters per second squared? So pick your favorite out of those 2. Right. What is that in centimeters per second squared? Is that 980 or 1,000? Right. Again, depending on how you finish the math by the end, right? Maybe one of those might be useful, right? All right. Write an expression for y in terms of x, right? So looking at this box, right? I'm going to give you guys 12 centimeters by 12 centimeters aluminum, right? And then you fold up the sides by some amount x. And that leaves you a base that's, y by y. Do you guys see that? It's going to be a square base, y by y, right? So as the size of the box, as x gets bigger, this base is shrinking, getting smaller and smaller. Right? So give me some math here. Right? Write an expression for y in terms of x. Right? Here, I'm gonna redraw that diagram I have over there anyway. So I've got a square of aluminum. Right? You start pulling up the sides. Right? So you pull it up the same on all 4 sides. Right? So you make a 3D box out of this. Make a 3D box. Right? So the whole thing is 12 centimeters by 12 centimeters. Think about like this distance here. Okay. And you fold up each side some amount x. That's going to leave you behind some value y. So that could be this right here, y. Right. So guys, what is y in terms of x? Y is equal to what? Is it 12 minus x, right? Isn't that what y is? You start off with 12 centimeters, subtract that x, you're left with y. Guess it? So it's 12 minus x, that's like 12 minus 2x. Right? And if you're keeping track of units, that's in terms of centimeters. Okay. Write an expression for the box boat volume in terms of x and y. Okay. Well, here, look at my diagram here. Okay. Here's the box altogether. It's going to be y by y is the base. It's going to be x centimeters tall. Oh, so guys, what's the volume of a box? Is it length times width times height? Right? Okay, so we could do that. It's the volume then is going to be length times width times height. That could look like that, right? But you know what? This y and this x are not independent of each other. you can express y in terms of x, and that's the next question. Combine those two expressions to come up with an equation of the volume of the box strictly in terms of x, right? So can I take this expression right here and substitute it right there? Right? So let's do it. Let's do volume of the box, then is going to be 12 centimeters minus 2x quantity squared all times x. Right? Right. Are you guys ready to FOIL? FOIL, first outside, inside, last. Right? This bit right here, right? Right. So this is going to look like volume is equal to C12 squared, so it's 144 centimeters being squared. Right? Minus C24x and then another 24x. Right? That's like 48x. And that's in terms of centimeters. Right? And then 2x quantity squared, right? And then negative, negative, it's positive. That's like plus, and then 4 x squared. Okay. Right? And then this is all times this x. Okay. Right. So then you're going to distribute. Distribute. Right. So now the volume as a function of x. Right. Right. So big picture is like as you fold up the sides of the box, the volume of the box changes. Right. The first little bit you fold up, you have a little tiny box, right? It's a real flat box, right? It has not very much volume, right? You fill it more and more and more, the volume of the box can increase until you start folding up too much. Like what if you fold up each side like 6 centimeters, right? At that point, the volume of the box goes back to 0. You have a little skinny pole, right? Something like that, right? So here's an equation you can just, in general, for any amount x that you fold up the sides, know what the volume of the box is going to be. It's going to be 144 x minus 48 x squared plus 4x to the power of 3. Right? Okay. Can you guys come up with that tomorrow? Right. Or if you're taking notes right now, then you're going to say, oh, yeah, of course. Okay. All right, so there you go. There's the volumes just in terms of how much you fold up each side. Right. Now, if some of you guys are in calculus, you might recognize that you can use calculus at this point to optimize, right? You say, what's the optimal amount you fold up each side to maximize the size of the box, right? That's one thing you do with calculus is like maximize, minimize, optimize, right? And this could turn into that, right? Or if not, that's okay too. You can do like trial and error. Say, okay, what if I fold up the box by each side, you try out 1 centimeter, 1.5, 2, 2.5, 3, 3.5, right? You try different values of x. Say, okay, what would the corresponding y be? You can use these equations we just derived, right? What was the total volume of the box, right? And then, okay, here's the connection back to the physics. What is the buoyant force that can hold, right? Remember, buoyant force would be density of the fluid times the displaced volume times gravity field, right? And if you put in so much weight that the box is just barely afloat, like the water level comes up just to the top of the box, but still floating. Right? You can do that with this aluminum box. Do that, right? Then the volume of the box would represent also the displaced volume of water. Right? So you can calculate the buoyant force. Right? So test this boat empirically. I'll give you guys some lab weights. You guys can come in the boat. Right? Now, how much weight can your box boat hold? Right? You guys good so far? Right, let's look at these graphs. I got 2 graphs for you guys. First one is box boat possible dimensions. What's y in terms of x, right? Which maybe it's just this equation right here, right? This equation you could graph, right? Is y in terms of x. I see y equals mx plus b looking for, right? Like if you don't fold up the sides at all, that's x is 0, and then each side y would just be 12. So like y-intercept, right? But if you take x all the way to 6, well, now each side is meeting the other side, right? And there's nothing left for y. Right? What that graph's going to look like. And then, no, this other graph's a little trickier. What is the buoyant force it can hold as a function of x, how much you fold up each side, right? So again, if you don't fold up any side at all, if x is 0, then the box has 0 volume because it's just a flat sheet. So I bet there's a 0.00 on this graph, right? If you fold up each side 6 centimeters, well, the square I give you is 12 centimeters. So you do 6 and 6. So you're just gonna like fold the square in half. You're back to 0, right? But somewhere in the middle, you're gonna get some volume of a box. I bet this is gonna be a curve that does something kind of like this. But I'll give you guys a hint here too. It's not a parabola. If it was a parabola, the answer would just be 3 centimeters. But the to maximize the maximum possible point force, right? But that may not actually be the answer tomorrow. It might not actually be 3 centimeters, right? I bet it might be, well, I'll leave it up to you guys to figure out tomorrow. But it's going to be some kind of upside down curve shape that's not a parabola. Okay. Finally, give you guys a hint down here. This might help too. Remember, got to reconcile maybe meters versus centimeters and grams versus kilograms. Right. Here's how you can convert volume in cubic centimeters to volume in cubic meters. That might possibly help. Right. So yeah, tomorrow I'll give you guys one of these pages, a square of aluminum, and a box full of water. And yeah, that'll be tomorrow's adventure. All right, so if you feel good about chapter 12 and 13 puzzles, go ahead and turn that into Gray Tray. If there's some you want to go check and turn in tomorrow, then that's okay too. And that'll be a wrap on the class.